Hello Physical Science, this is Mr. B and we're going to start section 2 today, and the title of this section is Heat and Thermodynamics. Now thermodynamics is going to be mentioned in the second half, so it's going to be mentioned in this next video in this section, so you're not going to need to worry about that term yet, and it sounds like a mouthful, but we'll explain it and it'll make a lot of sense when we get there. So the main part that we're going to focus on this video is heat and how heat can transfer in different ways. So there's different ways that heat transfers among different states of matter and things like that. So that's really what we're going to focus on in this section. So one example here to introduce us is that Newton's cradle. So I think one of you use that in your Rube Goldberg machine. It helps us to visualize a process that's known as conduction. One ball strikes the rest, and most of the kinetic energy is transferred to one ball on the end. So conduction is going to be one way that heat is going to move through different types of objects. So our first one, and hopefully with conduction you're going to remember a term that's known as conductivity that we talked about earlier in the year. So conduction is actually going to be slower in gases than in liquids or solids, and we're going to talk about that here in a little bit, and that's going to be like one of the big overriding questions is why does that occur? But to start, conduction is the transfer of thermal energy with no overall transfer of matter, which again we talked about that in kind of our first example within this chapter, that thermal energy and heat are transferred or can be transferred without any matter being transferred at all. So conduction in gases is slower than in liquids and gases, or than liquids and solids, because the particles in a gas collide less often. So with conduction, it's really going to be focused on how quickly thermal energy can just kind of pass right through a material. So since gases are so spread apart, it's going to be harder for thermal energy to to move through the particles, because the particles aren't going to be touching like they are in solids and liquids. So conduction occurs within a material or between materials that are touching. So two materials have to be touching one another for conduction to occur. In conduction, collisions between particles transfer thermal energy without any overall transfer of matter. So they don't move any matter, they just move throughout the particles. Again, the particles aren't gaining or losing any matter, they're not transferring it, it's just the thermal energy is passing through the particles in any form of matter. And a thermal conductor is a material that conducts thermal energy well or has a high conductivity. If you remember earlier on in the year when we talked about physical properties, I think we had someone hold a little glass piece of tube. We heated it up. Again, you couldn't feel any heat on one end. Then as soon as we changed that for a copper wire, the copper got hot and it made you drop it as soon as you felt the heat. That's because copper is a better thermal conductor, because the heat, that thermal energy that came from the flame, was able to pass through that copper much more quickly than it was able to pass through the glass. And the arrows here show how thermal energy is conducted away from the heat source in a metal frying pan. So again, the heat source is right here. Again, the heat is touching the metal pan, so the thermal energy is moving through the pan and here, and then it's moving away. It's again moving up the sides, moving through the chicken, moving up the sides, and eventually it will move up the handle. Notice how it's not really moving through the wooden spoon, which we will get to maybe why that happens in a second. So metals are kind of our best examples of a good thermal conductor. Again, we talked about that earlier in the year as well with conductivity. And when the frying pan is on the hot stove, the bottom of the metal pan heats up first, and then it heats up the metal handle last, because that's kind of just how it's going to flow. And the thermal energy is going to start where it's directly touching, because again the flames are directly heating the bottom of the pan. They're not directly touching the handle, so the thermal energy is going to have to pass through the pan, then into the handle. And then tile, this is kind of a more little interesting example. I have to think about this one a little bit more. Is actually a better conductor than wood, because a tile floor will feel colder than a wooden floor when both floors are at room temperature, and that's because the tile is actually transferring thermal energy more rapidly away from your skin. Now you'd think that maybe since the tile feels cooler, that maybe the heat isn't able to, or the thermal energy isn't able to pass through it, but the reason why the tile feels cooler is because it allows the thermal energy to pass through it and it moves it away from you much quicker, whereas wood, the thermal energy is in there, but it is kind of more trapped more. It doesn't move as quickly as it does through tile. So I think that's kind of a cool example here. And material that does not conduct thermal energy well, or that conducts it poorly, is known as a thermal insulator. And air is a very good insulator. Wool garments and plastic foam cups use trapped air to slow down conduction. So styrofoam is kind of a cool example here. One of the reasons why styrofoam cups don't heat up when you put hot coffee in them is because there's actually trapped air pockets everywhere throughout the styrofoam, and the air is a poor insulator, or it's a good insulator, I'm sorry, it's a poor conductor, so therefore it's going to keep that heat trapped in there. It's not going to transfer it through into your hands. So again, we've talked about these terms before. Again, now we're kind of relating it to thermal energy, not just whether or not it's a property of a physical or property of a substance. So that is conduction, one way that heat can transfer. Another way that heat can transfer, something that is known as convection, and this is the transfer of thermal energy when particles of a fluid move from one place to another. So a fluid, remember, is a gas or a liquid, so those are going to be the two states of matter that are involved in convection. And convection currents occur naturally in a lot of important places. They're responsible for ocean currents, different weather system, and movements of hot rock in Earth's interior. So convection plays a big role in physical science and actually in a lot of geology here, but we're going to kind of focus on more of just the basics of it. So the example they kind of give to, don't need to move that, to kind of help us understand what convection actually is, saying that passing sandbags along in a line is like transferring thermal energy by convection. So the arrows on the so that's just kind of an example to give us a little introduction, kind of a real-life example, a real-life analogy there. And the arrows in the oven show how convection of air works in an oven. And so again, we'll actually get an example to say how actually convection works rather than just kind of a more metaphorical thing there. A convection current occurs when a fluid circulates in a loop as it is alternately heated up and cools down. So what it means here, again, you probably are aware of this process, but you might not have just known that it's called a convection current. An example is in the oven. Is air at the bottom of an oven heats up, and therefore it expands and it becomes less dense. And the reason why it expands, we know, is because the particles are moving farther apart. And then the rising hot air cools as it moves away from the heat source. So right down here at the oven, the heat source is right here at the bottom of the oven, so that hot air is heating and heating, or the hot air rises and rises and rises, and by the time it reaches the top, it's farther away from the heat source, so it is going to cool, and then it is going to eventually sink back down. So as a result, the coolest air is at the top of the oven. So again, right here at its peak, the air will hang out here, and eventually it will cool back down, and then it will come, as it cools, it sinks, and then as it gets closer, it heats up more and then starts to rise again. So that's how convection works in an oven. Again, ocean currents are the same way. It's a constant mix of hot air rising up and cool air sinking down, and vice versa. Again, and tornadoes are often caused, again, that just happened not too long ago, by, again, hot air rising, cool air sinking, and that kind of gets going and going and going and going and going to the point where a tornado will start. So that's convection. So our last way is something that is known as radiation, and this is just the transfer of energy by waves moving through space. So all objects are going to radiate energy, and as an object's temperature increases, the rate at which it radiates energy is going to increase as well. So what that means is, to give us an example here, is when you stand to the side of a charcoal grill, so again, this is a good time of year for that, heat is going to reach you without convection or without conduction. Again, you're not directly touching the touching the charcoal grill. And again, there's no heating and cooling from a charcoal grill, but you still feel heat reaching you through the process, and that process is going to be radiation. So the sun warms you, or warms us all, by radiation on a clear day, because the space between the sun and earth has no air to transfer thermal energy. So when it has to pass through the space between the sun and the earth, again, hopefully you know the reason why astronauts have to wear those suits, because there's no real air, there's no oxygen, there's no anything up there in space. So the sun just The heat from the sun moves through the process of radiation until it reaches us on Earth. And then heat lamps used in restaurants are another example of radiation. Again, those lamps are not directly touching the food. Again, they're not creating hot and cold air differences. Again, it's just hot air moving down onto, or thermal energy moving onto the food to keep it warm. And the heating coil on a stove will radiate thermal energy, and the changing color of the red arrows indicates the farther you are from the coil, the less radiation you receive. So again, you can see this hot coil right here. The darker means that there's going to be more heat radiating out here, and as it gets less and less dark, that means less and less thermal energy is being radiated away. So those are 3 ways that thermal energy is transferred. Again, next week, or in our next video, it's going to be talking about something known as thermodynamics and how they relate to that. So till now, that's it for this video. Let me know if you have any questions.